Grudes? Sure. So looking at number 5, we first look for a greatest common factor. Should be easy to see there isn't one, because one is just variables and the other term is just number. Then we look at the number of terms. That has 2 terms in it. So if we look down the 2-term branch, the first thing we look for is a difference of 2 squares. That is a difference of 2 squares. So the exponent is even. There's subtraction. And then 64 I recognize as something squared. So I can write this as something squared minus something squared. Now x to the 6th is just 6 x's, right? So if I divide those up into 2 groups, you'd have 3 x's in each group. So x cubed squared is x to the 6th. And 64 we should just recognize as 8 squared. So I can factor that then using my difference of 2 squares rule. So far so good? Okay. Now I need to check each one of these. Oops, one of them is supposed to be a plus. Each of these results. So x cubed minus 8 is 2 terms. Down the 2-term branch, the first thing I look for is a difference of 2 squares. Clearly that's not a difference of 2 squares because the exponent is odd. And then I look for a sum or difference of 2 cubes. Well, that certainly looks like a possibility since it's x to the 3rd. So I'll try to write that as something cubed minus something cubed. Well, x cubed is just x to the 3rd. 8 I recognize as 2 to the 3rd. So my a is x and my b is 2. And my difference of 2 cubes factoring pattern, I guess I'll just write this down here so you can see where I'm filling things into. So I'm filling in here. A minus b is x minus 2. A squared is x squared. Plus, and then ab is 2x. And then b squared is 2 squared, or 4. Now we'll go and look at the x cubed plus 8, also 2 terms. Again, first we'll look for a difference of 2 squares. Nope. Next we'll look for a sum or difference of 2 cubes. Yes, well, it's a sum this time of 2 cubes, but it's the exact same values for a and b. And the sum of 2 cubes factoring pattern, again, I'll write that down so you guys can see where I'm plugging things into. Again, I'm plugging the values for a and b into that. So a plus b is x plus 2, and then a squared is x squared, then minus a times b is 2x, and then 2 squared is, or b squared is 2 squared, which is 4. And then if I check each one of these factors to see if I can do anything with them, the x minus 2 and the x plus 2 are linear, so there's nothing more I can do there. And then those 2 quadratic pieces both come from a sum or difference of 2 cubes, and I know that those won't factor anymore. So that would be as good as we could do for number 5. I think 5 was the hardest one on this sheet, my opinion. Because you had those 2 cubes things to deal with. Right, and those tend to be the hardest for you guys, it seems like. Other questions, you could go from this homework 2 that we talked about a little bit yesterday also, or you could look at the new homework 3. If there's questions on that, we can certainly take some from there also. On homework 3? Okay, sure. That's, oh shoot, I put this thing in the wrong spot. Great googly moogly. All right, hold on, I gotta do some surgery here. I'm gonna get to you, I promise. I just realized I put this in the wrong spot and I need to fix it. Okay. And you wanted to look at 6, you said, yes? Okay. I think this might have been the worst one from this homework also. Okay. So the first thing we do is we look for that greatest common factor. Clearly there's not one, right? And we do the number of terms. Well, that has 3 terms. So down the 3-term branch, first we check to see if it's in the quadratic form. It definitely is, right? Because we have degree 6, degree 3, and then constant. And then we look for the leading coefficient equal to 1. Yes, it is. So that tells us we can do the shortcut. So we're looking for 2 numbers that multiply to give us negative 216 and add to give us negative 19. Did you find those 2 numbers? No. Okay, well, the 2 numbers you need are negative 27 and positive 8. Okay. Again, the systematic way you could go about finding those if you couldn't see it by inspection is you just take the negative 216, divide it by 1, divide it by 2, divide it by 3, divide it by 4, divide it by 5, and you just then add up the 1 and whatever you got, the 2 and whatever you got to see if they match the addition problem. And eventually you'll find it, right? Hi there.
Hi, Mr. Cohen.
How are you?
Good, how are you?
Okay. Jack! They need you in the IT office with your tabby. It said it's an hour.
An hour?
It says that it's an hour. N-O-W-E-R. Here, you want to take that with you? I don't know if you need that or not.
Yeah.
I'll give it to you though, right? Yeah. Okay. Who are we talking to again? Hi, Emma, right? Okay. So you're good with how I got to those?
Yeah.
Okay.
What's the first thing you do? If you have to...
We want to worry about the multiplication problem first, right? Because there's only finitely many answers to that. The addition problem, there's infinitely many, right? Because you could have like negative 19 and 0, negative 20 and 1, negative 21 and 2, and you could just keep going on and on. Like there's no end to those. The multiplication problem, there's only finitely many checks though. Okay, so once we have that, we know we're going to have something minus 27 times something plus 8. That something, the variable that we're going to use, should match the middle term. So in our case, that's x cubes. You remember that? Okay. So then we need to check each one of those. So x cubed minus 27, that's 2 terms. Is it a difference of 2 squares? Definitely not, because the exponent is odd. Is it a sum or difference of 2 cubes? Yeah. So x cubed we can write as x to the third, and 27 we can write as 3 cubed. And then if I use my difference of 2 cubes factoring pattern, I'll write that down again so you guys can see where I'm plugging things into. So a is x and b is 3. Gives me that. And I do the same thing here, so 2 terms. not a difference of two squares. Sum or difference of two cubes. Well, yeah, that's a sum, right? X cubed we can write as x to the third. 8 we can write as 2 to the third. So my sum of two cubes factoring pattern is this one. Again, I'll write that down for about the 45th time. Maybe it just seems that bad because I'm doing this content in 4 classes. So it just feels like I'm doing it all the time. Maybe we haven't done it that many times in this class. It just feels like it. So a plus b is x plus 2. A squared is x squared, minus ab is minus 2x, and then b squared is 2 squared, or 4. And this is all still equal to 0. If I check these to see if I can factor any more, x minus 3 and x plus 2 are linear, so I can't do anything more with those. The x squared plus 3x plus 9 and the x squared minus 2x plus 4 are quadratics that come from the sum or difference of two cubes, so there's nothing more I can do with those. So I'm done factoring. So now I can solve by setting each of these pieces equal to 0. So x minus 3, we'll just add 3 to both sides. X squared plus 3x plus 9, we have to use the quadratic formula on. So I have x equals negative 3 plus or minus 3 squared minus 4 times 1 times 9, all over 2 times 1. 3 squared is 9, minus 4 times 1 times 9, that's minus 36. So 9 minus 36 is negative 27. Because we're squaring a negative, that makes an I. And then the square root of 27, I can think of as the square root of 9 times the square root of 3. So the square root of 9 is just 3. So I'm left with negative 3 plus or minus 3i root 3 all over 2. Yeep. The next piece I can just subtract. That's a relief. The next one, though, is again using I have to use the quadratic formula. So we have negative of negative 2 plus or minus negative 2 squared minus 4 times 1 times 4 all over 2 times 1. Negative of negative is positive. Negative 2 squared is 4. Minus 4 times 1 times 4 is minus 16. 4 minus 16 is negative 12. We make an I because of the negative underneath the square root. 12 is 4 times 3, so the square root of 12 is the square root of 4 times the square root of 3, and the square root of 4 is just 2, so we have plus or minus 2i, and then the root 3. And this can reduce, because if I write this as separate fractions, 2 over 2 is 1, and then the 2's there reduce, and I'm left with 1 plus or minus I root 3, and that's a long stinking problem. Like I said, I thought this was the worst one on here. Yeah, it was a lot to do, right? The solving really was kind of a gut punch at the end. It's like, oh my God, that factoring took so long, and now I have to solve this thing. But you guys will get better at it, right? It just needs practice. The solving parts in itself are not that bad. Sometimes simplifying the radicals are kind of a pain in the butt. But again, like we had talked about before, if you stopped like at these spots where you had the i's, once you got the I out of there, I would have been okay with that. Now that wouldn't be the result that would be on like a standardized test, but for this class I wouldn't worry too much about if the radicals are all the way simplified. As long as you got the i's. You know what I mean? I don't know if that's any kind of consolation there, Emma, but it was still a long problem. Fortunately, there wasn't that many problems on this sheet, right? Again, I try to be mindful of that. If the problems can be long and difficult, to not, here's 35 of these that are all like take a page to do. It's like that's a nightmare. Kill me now. Just wanted to try to pick enough so that you can see some of these different instances. I don't want them all to be like a million, a million of each instance. You just need to see a variety. So hopefully they were all unique enough to where it's like, okay, they're all a little bit the same, but a little bit of difference happened in all of them. So it's not like you're doing the same thing over and over and over again and you're ready to stab your eyes out. Unless you're just a stab your eyes out kind of person, Okay. Anybody else with questions from any of these groups on this recent homework? Okay. Okay. So that's -2, 8, -16. Okay. I copied that, right? Okay. That's fine. Thank you. Okay, first thing, GCF. Is there one? Nope. Number of terms. There's 4 there. So if I look down the 4-term branch, the first thing we want to try to do is grouping. So let's check that. So make my 2 groups. From the first group, we can take a greatest common factor of x cubed. From the second group, we can take a greatest common factor of 8. The key observation to make there is that those parts are identical. That tells us that the grouping is possible and we should continue to factor this thing. So when I take those x minus 2's out, I'm left with x cubed plus 8. Then I need to check to see if I can factor the x minus 2. And I'm not going to even bother running through the checklist there because I notice it's linear. So I know there's nothing I can do with that. The x cubed plus 8, though, maybe we can do something with. So that's 2 terms. And the first thing we look for, is it a difference of 2 squares? Obviously not, because the exponent is odd, right? And then is it a sum or difference of 2 cubes? Well, that seems likely. In fact, I think we almost did this problem. We might have done it exactly over here. Yeah, we did, right? So we did that one already. So I'm just going to copy that result since I've done it on this page already. If ever on a homework or a test or whatever, you've already factored something, you can just be like, refer to problem number 9. That's how I did this work, and not recopy it. You could recopy it if you wanted to, but like, I'm not about that life. So we can just do that then. And since this was factoring, we didn't have to worry about the solving part at the end, so we're just done. You're welcome. Does that feel okay? All right. You guys ready to start some newish stuff? So what we're going to do today is I'm going to point out to you some holes that we have in that factoring tree. And then we're going to start kind of talking about how we can start plugging some of those holes. Okay? So I want you to consider this polynomial, right? This is a factored form for some kind of polynomial, right? Let's multiply this out. So that's going to give us that. And then I'm going to get x cubed, 3x squared, 3x squared, 9x, 2x, and 6. Okay. So when we multiply that out, we get x cubed plus 6x plus 11x plus 6, right? So what this tells us is that clearly x cubed plus 6x squared plus 11x plus 6 is factorable, because we know its factored form right there, right? We started with its factor form. So that certainly is something that's factorable. Everybody agree with that? Let's try to factor x cubed plus 6x squared plus 11x plus 6 using our factoring tree. Okay? We're going to see that it doesn't work, but we're going to run through it and just kind of illustrate to you that it doesn't. So we look first for the greatest common factor, none of those. Number of terms, well, there's 4. So we try factor by grouping. So just like the previous example problem that we did together. So we'll take a greatest common factor from the first group, which would be x squared. And looking at a greatest common factor from the second group between 11x and 6, there really isn't one, but remember we can always take a 1 out. But now we can't proceed, right? Because those two pieces are not the same. So no, it's not factorable by grouping. So we would just say done. But it should be factorable, right? We know it factors because we started with the factored form. So there's still some incomplete parts in our factoring tree, right? Now, our factoring tree can handle a lot of situations, but it can't handle everything. What we're going to start working on now is filling in some of those gaps, some of those things that the factoring tree can't handle. And it's actually going to be a big process that we're going to start outlining here. So we're just going to take a small step in that direction today and kind of talk about the general idea of what we're going to start doing in these cases where the factoring tree doesn't work, with the caveat that we're not going to flush out all the details today. There's a lot of details in this process that we're about ready to outline that we're going to develop over the next several lessons. But for right now, for today, you're just going to get kind of like a broad strokes version, okay? So let's just write a little conclusion here. So again, we know that that thing is factorable, but the factoring tree didn't work with it, doesn't work on it. So we're going to have to develop some new methods. That's what we're about ready to do. So here's the big idea. So I'm going to do the initial example kind of numerically, and then we'll kind of do the example with a polynomial. But I want you, the idea is very simple, and it's almost so simple that it's easy to miss. So I really want to start with just like numbers rather than a polynomial so that it's hopefully easier for you to appreciate. So what if I asked you to factor the number 12? Well, you could observe that 12 divided by 3 is equal to 4, right? Now, 12 divided by 3 is the same thing as 12 over 3, right? Since fractions and division are the same thing. And if we multiply both sides by 3, then I get that 12 is equal to 3 times 4. This, at least, is a partial factoring of 12, right? You might be able to break down some of those numbers a little bit more, but that initial worked. So far, so good? Okay. So, in general, then, for a polynomial, p of x, and a factor of that polynomial, f of x, if p of x divided by f of x is equal to q of x, the big thing here is that the remainder is 0, then we can say p of x is equal to f of x times q of x. Where that f of x times q of x is our partial factoring. Now there's some big details left to be flushed out here. Does anybody see what the most important thing that's not addressed here in this example or this statement is? It's, how did I pick 3? How am I going to find that factor f of x? We're not going to deal with that today, but that's something that's going to take up a lot of time in the coming lectures, is figuring out tricks that we can use that make that not so much of a guess. Because if you're asking things that divide 12, like there's an infinite list of numbers I could try, right? Now 12, you probably figure, okay, nothing bigger than, I need something bigger than 1 and less than 12, because otherwise it's kind of trivial. But if that number was like 50,000 digits long or something, this is now an enormously difficult proposition, right? And that's essentially what you're working with a polynomial, because you don't have the ability to like order polynomials. Like, oh, I know if the polynomial looks like this, the only divisors have to be less than this. Like you just don't know that. So that's something that needs to be addressed, and we will address here coming forward. So let's kind of illustrate this with that polynomial that we have. So let's say we want to factor x cubed plus 6x squared plus 11x plus 6, given that x plus 1 is a factor. So using our method before, or that we've just described in general here, is I'm going to start with the polynomial division. So I need to take the polynomial I'm trying to factor. I'm going to treat that as the dividend. And the given factor I'm going to treat as the divisor. So we had done polynomial division. Right? This is kind of the initial setup. In our first question, we ask how many times does x go into x cubed? Or what times x gives me x cubed? You can think about it either way. The answer to that question is x squared. So then I multiply that to both pieces and subtract down. Before I do that, I want to distribute the negative though. So negative of a positive is negative. And then negative of a positive is negative. And now I can just kind of like add straight down. So x cubed minus x cubed is 0. 6x squared minus 1x squared is 5x squared. And then I'll bring that next piece down and go back to the top. And ask myself, what times x gives me 5x squared? Well, that's just 5x, right? And again, distribute. Write it underneath and subtract down. And distribute that negative. So negative of a positive is negative. Negative of a positive is negative. And we can just add straight down. So 5x squared minus 5x squared is 0. 11x minus 5x is 6x. Bring that last piece down. And then go back to the top. And ask ourselves, what times x gives us 6x? Well, that's easy. That's just got to be 6. And distribute through. Write it underneath, subtract down, distribute our negative. And we're left with remainder 0. So far, so good. Okay, so what this statement can tell me then is that x cubed plus 6x squared plus 11x plus 6 is equal to the divisor times the quotient. So now we have this partial factoring. Now the x plus 1 is linear. There's nothing more we can do with that. The x squared plus 5x plus 6, that's now a smaller polynomial. Maybe I can use my factoring tree to deal with that piece. Can we factor x squared plus 5x plus 6? We certainly should be. This looks like a semester 1 factoring problem, doesn't it? So we just need to find the two things that multiply to give us 6 and add to give us 5. What are those two things? So negative 1 and 6 multiply to give us negative 6, not positive 6. Well, that would be positive 6, but they'd add to give us negative 7, not positive 5. Three and 2. Yeah. And there is our full factoring then, right? So what's the main drawback here on this method? that this polynomial division process is just kind of tedious and time consuming and space consuming, right? What if we add a shortcut to that? Some cases we do, which is awesome. We call this shortcut synthetic division. So we can use this synthetic division shortcut that we're about to explain to you when the degree for our polynomial is 1, or the degree for our divisor is 1, I should say, and its leading coefficient is 1. So for example, let's go back to this polynomial that we've been using over and over again today. This is our division problem that we're interested in, right? Which one of these two polynomials is the divisor, the one on the left or the one on the right? The divisor is the one on the right. What's the degree for this polynomial, x plus 1? 1, right? Because what's the exponent on the x? 1. What's the leading coefficient of x plus 1? 1, because the number in front of the variable is 1. So we can do synthetic division. Everybody feel okay about what we have to do to check? Now, in terms of factoring, how often do you think we're going to be trying to divide a linear polynomial with leading coefficient 1? When we factor things, how often do we get stuff like that? All the time, right? Like all the factoring problems we get, we almost always have at least one factor that's a linear term to it, right? You guys notice that? So this is going to be really useful because it's going to, like we're going to be able to do this a lot, which is nice. Okay, so step 1, what we do is we set the divisor equal to 0 and solve. Step 2, we do synthetic substitution on the dividend with the answer from step 1. Again, that first number in the division problem is the dividend. Okay, so this is our synthetic division process. So let's go ahead and do that synthetic division process with this division problem that we've outlined here. So step 1, I'm going to take the divisor, set it equal to 0, and solve. Whoa, that was hard. Not really. Will it always be that easy? Yup. Because guess what? The divisor always looks like. Always has a degree 1, always has a leading coefficient of 1. It's going to be always trivially easy to solve those. That's wonderful. Step 2 is to do the synthetic division. So remember, the synthetic division setup kind of looks like this. The number on the outside of our synthetic division problem is going to be the answer to that division problem. And the numbers on the inside of my synthetic division setup are going to be the coefficients from my divisor. So in this case, it'll be 1, 6, 11, and 6. Everybody kind of remember that when we did synthetic division earlier? Remember I said that although this seems like a stupid thing to use to do substitution, it was going to be pretty useful going forward to do some other things. This is that other thing that I was kind of hinting at before. Okay. So the first step for our synthetic division is we just take that first number and we write it underneath. We take the number on the outside, multiply it to that number underneath, write it in the next open spot, and then add down. And we just keep repeating that process until we filled up all of our slots. So -1 times -5 is -5. We add down and we get 6. And then -1 times 6 is -6. We add down and we get 0. Division is done. Somehow this gives me the answer, which is pretty rad, right? That's considerably faster and considerably less space than the long division was, right? Way less opportunity to like drop a negative or do something silly there because all you're dealing with here are numbers, no variables. So these numbers at the bottom are going to tell me the information that I need to know to get the quotient. So this first number is the remainder. So we always start at the farthest right. The first number on the right is the remainder. This other, everything else, then, is the quotient. The next number to the left of the remainder is the constant term. The next number would be the x coefficient. After that would be the x squared coefficient. After that, if there was a number, in this case there's not, would be the x cubed coefficient, and so on and so forth. So what this tells me then is x cubed plus 6x squared plus 11x plus 6 divided by x plus 1 is equal to x squared plus 5x plus 6. Or the coefficients for that are coming from the result of our synthetic division. Yo.
Can I use the restroom?
You may. You're welcome. And this then would tell us that x cubed plus 6x squared plus 11x plus 6 is equal to x plus 1 times x squared plus 5x plus 6. And we've done that part going forward from there, right? Okay, let's do one more fresh one that we haven't done yet, right? We've beaten this single polynomial that we've constructed. For example purposes, we've done this problem like 4 times with this polynomial. So let's go back and kind of do this fresh with a new one from the beginning, so you can kind of see what, now that we've explained the process and we've kind of explored and built this process out, let's look at what the like streamlined version of this looks like, where I'm not digressing and going back and forth and like doing something one way and then doing it a shorter way, and like, let's just put it all together here and go through it a couple of times. Sound good? Okay. So again, I take sometimes these digressive paths to get to what we're looking for, because I want it to feel like a story. I want it to feel like a narrative where we're kind of exploring and learning something on our own. I think it gives more context to what we're doing. At the end, I'm going to tie everything back together in a neat bow and show you like the super streamlined process. But I think it helps you remember the process and understand the process if there's a little bit of narrative to it. And it feels a little less like just memorizing like a bunch of crummy steps. You know what I mean? So hopefully that would be the case here. Oops. So an example problem, we might ask to factor completely some polynomial, in this case x cubed plus 4x squared minus 11x minus 30, if x minus 3 is a factor. So for right now, I'm going to give you one of the factors. What we'll work on in the subsequent lessons, this chapter, is what do you do if I've taken that away? So like how would we figure out what to try to start with if we don't have a starting point given to us? And that's a part that requires a little bit of work. So that's definitely needs to be its own separate lesson. Okay, so what we'll do here, and again, I'm going to write maybe a little bit more than you would really need to, but I want to give like a little bit of context to what it is that we're doing and connect it back to the things we've already done. So this is what I need to start with, right? I need to start by taking the polynomial that we're trying to factor and dividing it by its factor. Everybody's okay with that? I can do synthetic division with this because my factor has leading coefficient 1 and degree 1. So I'll take that divisor, set it equal to 0, and solve. And then set up my synthetic division. So the first step is we bring that very first number down. And then we do 3 times 1. Write it underneath the 4 and add down. Then we do 3 times 7. Write underneath the negative 11 and add down. And we do 3 times 10. Write it underneath the negative 30 and add down. Now, in this problem, we're told that x minus 3 is a factor. So we know that we have to be getting a remainder 0 here. That must happen. If we don't get remainder 0 there, you've made some kind of mistake. Likely you've just made an arithmetic error in your synthetic division or made an error doing the synthetic division or something. However, if we don't know x minus 3 is a factor, thinking ahead, if it's 0, we know whatever it was a factor. If we don't get a remainder 0, then we know whatever it was we divided with was not a factor, and we have to try something else. So going forward, there will be a little bit of trial and error, and our determiner about whether something worked or not is the remainder there at the end. Okay. So using this, then we can say that our partially factored form of this is going to be our divisor times our quotient, which would be x squared plus 7x plus 10. Is everybody okay with that? And then we're just left to try to factor any of the pieces left. So obviously the x minus 3, that's linear, that's not going to factor anymore. X squared plus 7x plus 10, can we factor that? You betcha! What does it factor to? Again, that should be a polynomial that we did first semester that you can do in your head. Multiplies to give you 10, adds to give you 7. 5 and 2, so x plus 5, x plus 2, and we're done, right? Not too bad. In fact, I think in a lot of ways it's easier than a factoring tree problem. Now, is it possible that I end up with something that I have to go and use the factoring tree on? Oh yeah. Let's do an example where maybe that happens. Oops, I want black. And this will be our last example here. After this will be done for today. That's surprising. So we'll start by setting up our synthetic division, right? Because we can clearly do that. Everybody okay with that? Bring down the 1. 1 times negative 1 is negative 1. Add down that 0. 0 times negative 1 is 0. Add down that's 1. 1 times negative 1 is 0. Add down that's, or 1 times negative 1 is negative 1. Add down that 0. Negative 1 times 0 is 0. Add down that's negative 12. Negative 12 times 1 is 12. Add down that 0. So again, that's good. We have the 0 remainder. The rest of this stuff is the quotient. So that's our constant term, our x coefficient, our x squared coefficient, our x cubed coefficient, and our x to the 4th coefficient. So we have that our polynomial is equal to our factor times our quotient Everybody's okay there? Okay. Notice that x plus 1 clearly is not factorable anymore since it's linear. X to the 4th plus 12, or plus x squared minus 12. That has 3 terms. It's in the quadratic form. Its leading coefficient is 1. So again, we could use our factoring shortcut on this. The 2 numbers that multiply to give us negative 12 and add to give us 1 are negative 12 and positive 1. Multiplies to give negative 12, adds to give positive 1. They are -3 and +4. Very good. But remember, because this is in the quadratic form and not just quadratic, I'm not going to get x's in there. What variable am I going to have in there? X squareds. Everybody's okay there? Then I'd have to check the x squared minus 3 and the x squared plus 4 to see if those can factor further. Neither one of them is a difference of two squares, right? The first one, 3 isn't a perfect square. The second one is an addition problem, not a subtraction problem. Neither of them are a sum or difference of two cubes because the exponent isn't divisible by 3. So that's as good as we could do on that one. So you might have to use your factoring tree methods on that leftover piece. But all the problems that I've given you are ones that the leftover piece you have is something you can factor using your existing methods. So would that always have to be the case? No. And we'll see what to do later when we figure out how to pick possible factors next time. So we're going to stop here. This is going to be our ending point.